Hiya, I'm Barnaby. I'm the team lead of the Strathseds team for the Mach-25 competition, and this is our flight readiness review for the Stratosphere 4 launch vehicle. First off, our mission statements remain the same as the critical design review. We split them into primary, secondary, and tertiary, with our primaries to launch our 1 kilogram payload to 2 kilometers, and to deploy this payload from the launch vehicle and have it descend under a permanent recovery device. Our secondary missions being to use our AI models to analyze the video of land usage and classify it, as well as compress video to transmit and upscale when we receive it. Finally, our tertiary missions are to compare flight data from our Firefly Ultra and our COTS computers as a certification, and also to test the user experience of Firefly Ultra in a high pressure environment. Here is a table of the members that we intend to have attend the event. This is a total of 15 as we have paid for in our participation fees. Here is an updated Gantt chart of the project so far. We have had a fairly major delay with our fiberglass manufacture. The mechanical team will touch on that later. In fact, I'll pass straight over to the mechanical team to continue with a summary of the launch vehicle and the payload.
The design for the launch vehicle is mostly unchanged since CDR. There have been a few minor adjustments. Delays to manufacture due to the university labs have meant we've not been able to complete the launch vehicle at this point in time. More simulations have been conducted using RocketPi to determine drift distances. Our objectives are to 1. Deliver the payload to a 2 kilometer apogee, 2. Land within 750 meters of the launch site and recover. At this point in time, the launch vehicle is compliant with these following requirements.
The payload design has remained unchanged for the most part, with only a few small changes since CDR. There have also been some manufacturing delays due to issues with the university labs. Since then, we've conducted further simulations using RocketPi to determine drift distances. Our three main objectives are to deploy apogee and land within 750 meters of launch site, live stream video during descent, and use AI to analyze video of land usage and classify it.
This is the current overview of our payload requirements. If there's any major work that needs to be done at Mach-25 Air Base, we won't fly. What we're expected to have to do at Mach is utilise our launch day procedures as well as the day before procedures. So check parachutes and recovery harnesses, integration of payload and computers, motor integration on launch day. Note, the assembly is complete and an ejection charge is plugged. The only other thing we'd be willing to do is like final touch-ups on paint or other non-critical work. For Mach-25 this year, we are using 3 parachutes, a 72-inch main, an 18-inch drogue, and an 18-inch parachute for the CANSAT. Based off both the actual masses of parts we've manufactured and the approximate masses of things we are yet to acquire, we have found that these would be appropriate. For now, we're expecting about 700 grams of ballast, though this will change as we get more accurate masses as things are manufactured. We have a diagram of how the parachutes will work above, and they will be attached to each part of the rocket using quick links, U-bolts, and I-bolts.
There have been no significant changes to their vehicle's design since the CDR, just a few minor adjustments of how some computers have been mounted. Due to issues with our university labs, we've been unable to get our fiberglass sheets cut by the university like we were expecting. We have found an alternative, but this has delayed our manufacture as we don't have our bulkheads and fins yet. At the time of recording, we have just been told the fiberglass has been cut and we'll be ready and we'll pick it up as soon as possible so we can continue with our manufacture. All airframe and coupler tubes have been cut to the correct lengths and the ends sanded. The holes to be put in the airframe and coupler tubes will be made once all the bulkheads and things that need the holes have been put in so that we can make sure that they're in precisely the right place. As previously stated, the collection of our centering rings and bulkheads has been delayed. Once we've received these, we can put the holes for wires and things through the bulkheads, and we can assemble the motor mount assembly. We have also begun our hand layups. We have done one layup of the ejection piston, which is just awaiting one hole to allow the shock cord to pass through. We are also awaiting just one part of the mold to lay up our nose cone, which once that has been completed, the nose cone assembly can be made once we have got our bulkheads from the water jet cutting.
There have been no design changes to the AV bay since CDR, however it has been printed with the adjusted tolerances. PLA bulkheads have been printed and test fitted, but with the delay with the fiberglass, we're still waiting for the fiberglass to arrive so we can fully construct the bulkheads. Battery removal tabs and contacts have been added with hot glue. Wiring will be added once the RBF board and Firefly Ultra arrive. The final holes in the airframe for the RBFs and the camera will be cut once all of the tubes are together and stacked. Slots still need to be cut for the rotational lock in the coupler, and the camera faceplate still needs to be printed. Once again, due to the delays in fiberglass, we've not been able to complete all our testing or requirements, such as the following ones.
Due to the situation with the fiberglass components, our ejection testing has also been delayed. We are aiming to do this on a SARA launch date of the 14th of June. Our simulations showed the rocket would have a maximum acceleration of 194 meters per second squared, which, given our launch mass of 8.5 kilograms, would lead to an axial loading of approximately 1,700 newtons. In keeping with the guidance provided, this means our airframe should be designed to withstand around 343 kilograms axially. We have been unfortunately unable to test this. However, given our material choice of G12 fiberglass, we are confident the vehicle is overspec'd for this and will be able to handle the loads fine.
So, as a brief overview on the electrical side of things, our most important astronaut flight computer, the Firefly Ultra, has suffered a few delays in the design stage, but we have all sent it to manufacturing and assembly, and we're on track to actually finish assembly once we receive it next week and do a test flight during the National Rocketry Championship. We've been going over testing using our development board, so all the new parts on board the Firefly Ultra, as compared to our previous years and previous generations of flight computer, have already been tested, and we're not really expecting anything new to pop up with the integrated design. But we will have time between NRC and Mach to actually implement any fixes that we might need to find. As for the remainder of our orders that we're still awaiting, two of them are not flight critical and we can absolutely fly without them. That being our remove before flight board and our ground station computer, which we can, for the former, replace with screw switches if testing does not prove successful, and the ground station can be easily replaced by another instance of a Firefly Ultra. The flight computer that will be used in our CANSAT, especially the streaming board, we'll be using for AI processing and a test of streaming video live, is also in that same batch of production. We will be expecting to receive them in the next 2 weeks. As you can see here, most of them actually finished production of the PCBs. We're just waiting to finish the assembly portion. The streaming board is mostly composed of COTS parts as for the compute module, and we will be receiving it fully assembled, so we will not need any additional steps as far as manufacturing goes, and all integration will be either mechanical or software based, but we have already been working on the software using a compute module that we have here with an IO board.
In terms of the AI that we're going to put on board the CANSAT, so far we've replicated the work in this paper, Extreme Video Compression with Prediction Using Pre-trained Diffusion Models. We've replicated this work and we're working on porting that to the Raspberry Pi CM5 for real-time streaming. In terms of land use classification, we've not quite got around to implementing that yet. Since the CDR, the Open Rocket model has been ported over to Rocket Pi for more accurate drift analysis. The drag curves for the analysis were obtained using RAS Aero 2. On the screen here is a comparison between the Rocket Pi model and the Open Rocket model. There are some very small discrepancies, but I'll be checking on that as soon as I can. Here we have a stability time plot in Rocket Pi. This does go ever so slightly above the 2.5 maximum. This can be solved with a little bit of aft ballast. Next, the impact speeds for the CANSAT and the rocket are estimated to be 12 and 6 meters per second respectively. This is well within the guidelines. And here we have a matrix showing the impact location of the CANSAT at varying wind speeds and launch angles. At the bottom left is 20 degrees, but it's a big number, so you don't need to see it anyway. And then on the next slide, we have the same matrix for the launch vehicle. Finally, this matrix shows the legal launch configurations we have. This shows that we have a legal configuration for every wind speed required of us. Finally, using Rocket Pi, we can show our trajectories on a Google Earth map So this is a launch for tomorrow, using tomorrow's GFS forecast, showing the wind profile on the right-hand side. Finally, for recovery, we have a Sinotrack, a Find My device, and Firefly Ultra on both the rocket and the CANSAT. This triple redundancy on both vehicles should give us the optimum chance of recovery. In addition, we can use Monte Carlo simulations using RocketPy to give a more accurate estimation of where we're going to be landing.
These are our concept of operations. The rocket will be prepped at most 2 hours before launch following integration procedures. This would be done without black powder. Once at the launch site and with RSO instruction, the ejection wells can be filled and the parachute bay is secured to the AV bay. At this point, the rocket can be stacked. The motor can then be integrated before launch. After that, we would follow this concept of operations.
To briefly touch on the outreach we've done so far this year, we've had a couple of stalls at a few conferencing events, including the UK SEDS regional event for Scotland hosted by Glasgow Uni Orbit, as well as the National Student Space Conference at the University of Leicester, and finally the Strath Aerospace Innovation Society's Aerospace Networking Night. We did also try and have an event through Glasgow Tech Week, collaborating with the Glasgow Chamber of Commerce, but unfortunately this has fallen through. So to summarise what we've done since the Critical Design Review, our airframe tubes have arrived, so we've started some construction on the mechanical side, but there's some unexpected delays in the fiberglass sheet cutting. We've ordered all the PCBs we require for both our avionics system as well as our payload, and final versions of some 3D printed components have been completed. I'll hand over to Luke and Julia from the mechanical and electrical teams to wrap up what they've done.
Once the waterjet cut parts have arrived, the remainder of the manufacture can take place. This includes drilling holes in the airframe and bulkheads, gluing in the bulkheads and fins, and attaching the motor mount tube. The nose cone layup needs to be done once the mould has been printed. The final holes need to be drilled in the ejection piston, nose cone and airframe, and we also have to print the flyaway rail guides.
So to quickly summarize, as far as the remaining work to be done on the electrical side, we'll be completing assembly of Firefly Ultras and doing a test flight at the National Rocketry Championship, and while gathering all the data from that flight, we'll use it for any last fixes that we need for the Mach flight. And as far as the steering board that we'll be using inside the CANSAT, we are waiting manufacturing, but as already mentioned, it will be arriving in a fully assembled state, so any work to be done there is purely software based.
Finally, just to acknowledge some of our supporters, I'd like to thank Strath Union, the Strathclyde Alumni Fund, ANSYS, SolidWorks, Altium, RS, and JLC PCB for supporting us financially throughout the project, as well as JetCut, based down in Glengarnock, for helping us cut our fiberglass last minute.